Hi, we're the Sensory Regulation System team, and our members include Jimena, Jay, Ploy, and Andriana. We are graduate students from IDM and ITP. Visual description: a picture of the final design of our prototype, including the vest on a mannequin and the wristband displayed on Jimena's wrist. A video of the wristband on Jimena's wrist attached to the circuitry. The LED lights are flashing. A close-up video of the rotary system attached to the side of the vest. The motor is wrapping the fabric around a shaft, tightening the vest. The Sony headphone desktop interface for controlling ambient sound and noise canceling, adapted from open source code. Sensory overload, caused by sensory processing disorders, is a condition in which an individual's sensory systems are overwhelmed by an excessive amount of stimuli, leading to difficulties in processing and responding to sensory input. For some, this can be mitigated with the use of deep pressure therapy. Deep pressure therapy, or DPT, leverages touch information to stimulate specific receptors that feed into the sensory processing pathways in the brain and trigger a calming reflex in the body. Visual description: an illustrated diagram of the touch receptors. Therapeutic tools such as swaddling, massage, weighted pressure vests, and weighted blankets are commonly used to provide deep pressure stimulation. Visual description: a child wearing a blue weighted vest, a weighted blanket, and an image of a child being wrapped in a deep pressure sleeping bag by a clinician. Research indicates that deep pressure therapy is associated with a reduction in anxiety for certain individuals. Results of a study on behavioral and physiological effects of deep pressure on children with autism indicated a significant reduction in tension and a significant reduction in anxiety for children who received deep pressure. Another study with individuals on the autism spectrum demonstrated that deep pressure appears to be of immediate benefit to this population. A third study, titled Physiological Effect of Deep Pressure in Reducing Anxiety of Children with ASD During Travel. This study concluded that deep pressure therapy decreases the physiological arousal of children with ASD during travel on public transportation. Their heart rate was significantly decreased during treatment compared to the baseline. Visual description: an illustration of a person who appears overstimulated and experiencing sensory overload. Next to it is a heart with an exclamation mark to signify an increased heart rate. In a situation with high stress, sometimes it is hard to communicate with words to those around you or recognize your own need to regulate your anxiety levels. With an automatic monitoring system, your needs are made clear by your body's response nonverbally. This system is designed for those who struggle with sensory processing challenges and/or who benefit from deep pressure therapy. The noise-canceling aspect of our system will allow for further sensory regulation, as loud noises might contribute to or cause higher stress rates. Visual description: sketches of each of the components in our system. The wristband with a Bluetooth microcontroller, LED light, and haptic motor. A sketch of the vest itself and the shaft and motor to be attached. Alongside these is a picture of the shaft and motor rotary system attached to the final vest prototype.
What is the concept? The idea is to regulate stress using deep pressure through compression. The compression is triggered by the pulse sensor on the wristband. Once it detects an increase in pulse, it will communicate with the motor via Bluetooth connection, and the shaft will begin ratcheting down the straps attached to the vest.
Visual description: an illustrated heart with arrows pointing down to indicate a decreased heart rate.
The result: the tightening of the vest will have a therapeutic effect and lower the stress levels and pulse back to a steady state. Our system covers 3 different sensory modalities: touch, visual, and sound. We decided to include these since after our first user test, users indicated that these are the most impactful when experiencing sensory overload. When designing the tactile aspect of our system, we decided to include compression and haptic feedback. Our visual component in the system is an LED light on the wristband to notify the user of an increase in pulse rate. Finally, for sound, we decided to include a noise-canceling feature that the user can enable on their headphones that will respond to the system.
The system can be worn under or over clothing depending on the user's needs or preferences. The sleek design allows the users to wear it outdoors or at home comfortably. If the user has a caregiver, the LED lights will allow them to be aware of their stress levels. On the other hand, if the user is looking for discretion, the lights can be turned off. In addition, users have the option to receive haptic feedback from the wristband to let them know that the compression is going to start during a high-stress period. Our prototyping process. We started by rapid prototyping with cardboard, craft paper, and string to visualize how the vest would work.
Visual description. A video and photo of our low-fidelity prototype. Strings laced through the paper vest are pulled together to simulate compression.
Our initial idea was to use an automatic lacing system for compression. The inspiration for automatic lacing was from Nike Mag and Nike Adapt BB shoes.
Visual description. A video of the Nike Mag shoes and self-lacing system. The laces automatically tighten when the user steps into them. Alongside the video is a picture of the Nike Adapt shoes and a picture of the lacing patent.
After researching and going through the Nike patent, we found a manual lacing system that works similarly, and tried to automate it by connecting a stepper motor to the rotary system.
Visual description. A sketch diagram of the lacing system in the vest with a picture of a stepper motor attached to the laces. To the right is a picture of the lacing product we found, and below is a video of how it works. The mechanism is a quarter-sized dome that houses the laces. When a user spins the dome clockwise, the laces retract into the dome.
We found issues with the amount of friction created by the lacing mechanism and would limit the amount of compression because the laces would originate at one point instead of seamlessly compressing across the torso. After several weeks of iterating, we decided to change our approach and make a more efficient compression device. To user test, we created a medium fidelity prototype made with fabric.
Visual description. A photo of our fabric prototype on a mannequin. Jimena and Jay stand proudly beside it. Visual description. The automatic corset made by Luis Katsovitz is shown here. The corset sits on a mannequin and is tightened with the motorized lacing system, followed by a video of our prototype.
Inspired by the work of the fashion designer Luis Katsovitz, we designed our final rotary compression system using a servo motor attached to a 3D printed shaft that wraps the fabric of the vest around it to create compression. We tested many different sizes and materials such as PLA and TPU for the rotary compression system.
Visual description. Pictured is a 3D model of the shaft, a picture with 4 different printed prototypes, a video of the model being printed, and one of a working prototype with the shaft spinning.
User test and feedback. After our first user test, we collected insights on what our target users needed and wanted. Regarding the haptic feedback, some users were comfortable with it, while others were concerned it could trigger more overstimulation. Hence, we make it optional. Users also expressed privacy concerns about the visibility of the LED lights that may cause unwanted attention. Another preference indicated was that users wanted to be able to wear the vest under their clothing with skin-to-skin contact. We found from the user test that many participants would also benefit from connectivity to noise-canceling headphones. Learning moment. The biggest lesson we learned was to practice non-attachment to our original plan. We also learned about time management, as things often go wrong in the prototyping process. Being comfortable asking for help was ultimately very important to be able to complete our project. Things that don't work. ESP32 microcontrollers gave us a chance for wireless communication. However, it is not compatible with many sensors and motors. We changed our initial proposal of using stable motors to servo motors. We also had issues with the external batteries and their compatibility with the circuit. Next steps. For the next steps, we would like to fully integrate the noise-canceling feature into the system, as well as to make the system fully wireless and streamlined. We would also like to add more points of compression to the vest, such as the shoulders, as our current system only addresses the torso.
Our team would like to thank the Makerspace Design Lab for making the prototyping fund possible, and to Professor Lauren Race for supporting our work. And thank you all for listening.